Okay, open delta or VV connection. So what is this open delta? Let us see. When a bank of three single phase transformers are connected in connected in delta delta, supplies the three phase balanced load, then each transformer carries 1/3 of the total load. Okay, so here the connection is delta delta. So we are using a bank of three single phase transformers, not a single unit of three phase transformer. Okay, so in this case each transformer will carry 1/3 of the total load. Okay, assuming we are having balanced load system. Okay, now if any one of these three transformer gets damaged accidentally or any other way, then what happens? Then we can remove that faulty transformer from the three phase bank, and we can still supply a three phase power to the load, and this will be at a reduced level. Reduced level means the capacity of the remaining two transformer, we cannot use their full capacity. We will be able to supply at a reduced level, means we will not be able to use the full capacity of the two remaining transformers. That we will see later on. Okay, so then after the removal of this faulty transformer, this new formation, that is called the open delta or VV connection. Okay, so such a connection after removal of one of the transformers from the conventional delta delta configuration is called the open delta connection or VV connection. Okay, so it will look like this. Okay, so this is open delta or VV connection. So thus in open delta system, instead of three single phase transformer, two single phase transformer can be used to form a bank and supply three phase power to a load. See, we are using only two transformers in open delta or VV connection, but still we are capable of supplying three phase balanced load. Okay, so three phase supply system will form with these two transformers only. Okay, that is the most interesting part of this connection. So this is normal or healthy delta delta connection, we can see. So if we remove one of the phases, suppose this C phase transformer is removed from this delta delta connection, then this open delta connection will form. Okay, so here we can see from the primary side that we are still supplying three phase balanced supply, or we are still giving three phase balanced supply to the primary side. See, this is three phase balanced supply which are still connected to the primary side. So here this is one point of supply system, this is another point, this is another point. So three terminals are there. So we are giving three phase supply to two transformers. Okay, primary of two transformers who are connected in delta formation. So these two windings are connected at this point. Okay, so as we are giving three phase balanced supply to the primary, we will get a three phase balanced output from the secondary. Okay, so here we will get three phase balanced output voltage. Okay, that we will see how this three phase balanced supply is formed. So here VAB, this is the high voltage side we are assuming. So VAB, that means this point and this point, this voltage is equal to V phase angle 0 degree. So here in case of delta delta connection, phase voltage and line voltage are same. So VAB, actually this is line to line voltage, but that is also the phase voltage. Okay, so VAB is equal to VP angle 0 degree. We are assuming VAB as the reference phasor. So with respect to that, VBC is equals to VP angle minus 120 degree, and that is the voltage between terminals B and C, and VCA is equal to VP angle plus 120 degree. So we are getting we are giving three phase balanced supply with a phase sequence of A, B, C. Okay. So this is the supply voltage we are giving to the primary side. Now the secondary side. Here only transformer A and B, this one and this one, A and B are healthy transformer now. C phase transformer is removed. So voltage transformer occurs in these two transformers only. That means the flux will be produced by this transformer and this transformer, I mean these two windings only, and those fluxes will link with this windings and there will be induced EMF. So voltage transformation occurs between these two transformers only. There is no third transformer. Okay, so how this transformation will occur? It will occur according to this ratio, that is VAB by V small ab. That means this voltage and this voltage, their ratio will be equal to VCA, that means this voltage and this voltage is equal to, this is V phase, V primary, and this is V secondary. Okay, VAB, VAB and VCA, their magnitudes are equal, V phase. Okay, and V in secondary side, V phase is equal to Vs. Suppose the secondary voltage is denoted by the symbol Vs. So their ratio will be equal to primary turns per phase divided by secondary turns per phase, which is the turns ratio. Let us assume that turns ratio by A. Okay, so primary turns per phase divided by secondary turns per phase is equal to A. That is the turns ratio. Okay. So using that, we can express the secondary voltages in terms of the supply voltage, that is V small ab is equal to V capital AB from this equation by A, and we know VAB, this phasor, is equal to VP, that is V phasor or V primary, divided by A angle 0 degree. We have assumed this as the reference phasor. So V small ab is equal to, and this VP by A, this is equal to Vs. Okay, VP by this A will give you Vs. So Vs angle 0 degree. So VAB, this phasor, is equal to V secondary angle 0 degree as per this transformation ratio. Then VCA, that is equals to V capital CA by A, that is equals to VP by A angle plus 120 degree, which is Vs plus 120 degree. Okay, so we are getting two voltages across AB and CA terminals. Now what about the terminals B and C? So VAB equals to this, VCA equals to this. Though this phase is not here, still there will be potential difference between B and C terminals, isn't it? B and C are not at same potential. Agree?
Yes, sir.
So there will be some potential difference between these two terminals B and C. Okay, so that means if we measure between, if we place some voltmeter across these two terminals, we will get some voltage reading. Okay, so what will be the voltage? That voltage, let us see. So VBC is equal to potential of point B and potential of point C. Let us assume that potential as VB and VC. Okay, so VBC equals to VB minus VC, which we can write like this. We're subtracting one VA and adding one VA, so no change. And after rearrangement, we can write like this. And VA minus VB, what is this? This is VAB. And VC minus VA, what is this? This is VCA. So we can write like this. So these two are line EMFs or phase EMFs, that as because this is a delta connected system. So putting the value of VAB and VCA in complex form, we can write this, or in polar form. And after simplification, what will we get? Let's see. So this is the complex form or trigonometric form, and after simplification we will get this, which is this in polar trigonometric form, and that is equal to VBC equals to VS angle minus 120 degree. You can do this calculation by yourself. So VBC is actually VS minus 120 degree. So what is the meaning of this? Meaning is that we are getting balanced three-phase output across the secondary, though the third transformer, that is the C-phase transformer, is absent. So the three-phase balanced voltages are, output voltages are VAB equals to VS angle 0 degree, VBC is equal to VS angle minus 120 degree, and VCA equals to VS angle plus 120 degree. Is it clear?
Yes, sir.
Anyone having any doubt about this output? With two transformers only, we are still getting three-phase balanced voltage output from the secondary terminals. Okay, so this is the output voltage expressions. So from this we can observe that these three secondary line voltages form a triangle, or we call it a triad of three balanced voltages of equal magnitude and displaced from each other by 120 degree. That means it forms a balanced three-phase supply system. Okay, so therefore we can conclude that with two transformers only, it is possible to obtain a three-phase balanced set of voltages in the secondary with no difficulty in supplying a three-phase load. So as we are getting three-phase balanced supply as output from the secondary, so we can connect three-phase balanced load or three-phase load. Okay, no problem with that. Now the next is KVA delivered. Okay, so here let us consider one transformer, I mean which is having all the three transformers present. That means a three-phase bank with delta connection, and all the phases are healthy. Okay, so by this transformer we can deliver 60 kVA load. Okay, so next here power carried by each transformer will be 1/3 of this 60 kVA, so that is 20 kVA. no problem. Now one transformer is faulty. So what happens? Two are still working as in open delta connection or VV connection. So that is the open delta mode. And now the question is, how much total power can be delivered by this open delta connection or VV connection? Can we supply 2/3 of this 60 kVA? That means 40 kVA. That is my question. This system is capable of supplying 60 kVA. Now one transformer is removed from the system. So the system runs as a open delta connection or VV connections connected system. So the question is, how much total power can be delivered by this system? Is it the 2/3 of the previous capacity, that is 40 kVA? What do you think? Anyone?
Sir, it will be slightly more than 40 kVA.
Slightly more? What are you saying? We can see capacity of each transformer is 20 kVA. So only two are present now. So it is a natural thinking that we will be able to supply only 2 into 20, that is 40 kVA. But my question is, can we be able to supply that much of load, 40 kVA? And the answer is no. Okay, why is it so? Let us see. So for healthy delta, that means proper delta connection, VL equals to V phase, we know, and IL equals to √3 I phase, that we know. Therefore the total kVA rating of a 3-phase delta connected bank will be √3 VL IL. So this is the capacity of a 3-phase bank connected in delta system, delta connection. Okay, so this is P healthy, that is equals to √3 VLIL, and putting the value of IL and VL, we get it as 3 V phase I phase. That means 3 into capacity of each transformer. Capacity of each transformer is V phase I phase. Okay, so if we multiply it by 3, we will get the total capacity. As simple as that. Okay. Now with one transformer faulty or removed, the connection is open delta or VV. So voltages are still balanced. We have seen that. So here VL equals to V phase. But what about the current? Is it still IL equals to √3 I phase? The answer is no. Okay.
More than that.
Sorry?
IL is slightly more than that, I think.
No, not more. It will be less. Let us see. So since the 3-phase load is getting balanced voltage, it will draw balanced 3-phase line currents from the open delta secondary. Okay, so it will form a 3-phase balanced current also. Okay, so what will be the current? Load drawing balanced 3-phase line currents. See here, IA, IB and IC are 3 line currents, but only 2 phase currents are present. So there lies the unbalance between this phase current and line current equation. That means we cannot express it like a healthy delta system, that is IL is equal to root 3 I phase. We cannot apply this equation here because only 2 phase currents are present and 3 line currents are there. So we cannot have this kind of equation here. Okay. So how to handle this kind of situation? So let us see, here 3 line currents are present and they are balanced. Now the magnitudes, what will be their magnitudes? Line currents from the 2 healthy coils, that is line B and C, are IB and IC. So these are the two currents from the healthy phases. Okay. And since one transformer is damaged, the total load must be reduced. So we cannot supply, suppose as per our previous example, we cannot supply 60 kVA, that is for sure. So now the question is, can we supply 40 kVA? That we have to check. Okay, this 60 kVA we cannot supply, that is for sure. So otherwise, if we supply this 60 kVA, then what happens? The 2 remaining transformer get overloaded and they get damaged. They will get damaged. Okay. So the 2 line currents IB and IC should not be more than the rated currents in the corresponding phase coils. That means this IB, that means the line current IB cannot be greater than IBA, or IC cannot be greater than IAC or ICA, whatever. Okay. In case of healthy delta connection, the line currents are more than that of phase currents because they are the in case of delta connection, the line currents and phase currents are not same. Since phase currents are less than line currents, so they are capable of handling more amount of line currents. But in case of open delta connection, that is not true. Okay, so here line currents and phase currents are same for the 2 healthy phases. So if we supply the previous amount of line current, that means the line current required to supply 60 kVA, then that same amount of line current will flow through these remaining 2 phases, and that is not permissible because their insulation capacity does not permit that. Okay, if we still supply 60 kVA amount of load, then the line current, then the value of current will be so much high that these 2 transformers will get damaged. Is it clear? Any doubt? Anyone?
No, sir.
Okay, so it is obvious that we cannot supply 60 kVA. So next is, can we supply 40 kVA or not? So here line current, let us consider this is line 1. So IL1 is equal to IB, which is same as that of IBA, though they are in opposite direction, but still they are equal. So that is equals to I phase angle 0 degree. Okay, this direction was the previous direction, that means while they were in healthy delta delta connection. So now this direction will change as per the new open delta connection. So IL1, let us assume that as the reference phasor, so which is equal to IB, that is equals to the phase current IBA, so that is equal to I phase angle 0 degree, and IL2 is equal to IC, which is IAC, that is equals to I phase angle minus 120 degree. So the next current. Okay, so the third line current IL3, which is IA, must be equal to minus of IB plus IC. to satisfy KCL. If we write KCL equation at this node, so what will be the equation? We can see all the three currents are outgoing. So IA plus IB plus IC is equal to 0. So from that we can say that IA is equal to minus of IB plus IC, isn't it?
Yes, sir.
So therefore, again, by performing similar calculations as that of voltage, we will get that IA will be equal to I phase angle 120 degree. So the three currents are IA is equal to I phase 120 degree, IB equals to I phase angle 0 degree, IC equals to I phase angle 120 degree. So this is also a balanced three phase current. Here we have considered the B phase as the reference phasor. So if we consider A phase as the reference phasor, then all other phases will get shifted by an angle of 120 degree. So in that case we will be writing this equation as IA equals to I phase angle 0 degree, IB equals to I phase angle minus 120 degree, and IC equals to I phase angle plus 120 degree. So these are basically same, because this phase shift is relative, it is not absolute. Okay, whatever uh, this phase angle lie between any two phases, that is with respect to some reference phasor. So if the reference shifts, this uh, angle will also change. Okay, so these three currents are also making a balanced current system. So the three secondary line currents are thus seen to form a balanced set of three phase currents with same magnitude, that is I phase, and displaced from each other by 120 degree. Okay. Therefore, we can observe that to prevent overloading, the two remaining healthy coils, the line currents cannot be more than that in the individual phase coils, that I have already mentioned. So here IL equals to I phase for the secondary line currents. We have seen that IA is equal to I phase, and with some angle IB is equal to I phase, and IC equals to I phase. So all the line currents are equal to I phase. Okay, so in case of open delta or VV connection, the relation is IL equals to I phase, not IL equal to root 3 I phase, isn't it?
Yes, sir.
Okay, so from that now we will be able to the load or kVA delivered by an open delta or VV connected system. So here P open delta is equal to root 3 VLIL, which is root 3 V phase I phase, unlike the health delta system, which was 3 V phase I phase. Okay, so the kVA capacity has reduced to root 3 V phase I phase from 3 V phase I phase, okay. So we can see the load carrying capability has reduced. Therefore, the factor by which this capacity has reduced is 0.577. That means we can conclude that when one out of the three transformers in a delta delta bank fails, it is still possible to supply a three phase load, but with a reduced capacity of 57.7%, not 66.6%. What is the significance of this? That is 2/3. That means we cannot supply 40 kVA also. It is still lesser. Is it clear now? Why we cannot supply 40 kVA also?
Yes, sir.
Anyone else having any doubt? Okay, so it means that when one of the three transformers in a healthy three-phase delta connection gets damaged, then with open delta mode, it is still possible to supply balanced three-phase power, but the load current must be reduced to 57.7% of its original value. Okay, then only we will be able to supply the existing load. Okay, so that is why it was claimed at the very beginning that we can supply three-phase loads with this open delta connected system, but at a reduced level. Okay. So next is utilization factor or rating factor. What is the meaning of this? As we can see, the ratings or the capacity of the two existing healthy transformer is 2 V phase I phase, but we cannot use the whole or the full capacity of these two transformers while connected in open delta connection. Okay, so this ratio of actual used capacity and actual used capacity or its actual capacity and its actual capacity, that is called the utilization factor. So utilization factor is actual kVA capacity of open delta total installed capacity of the two healthy transformers. Okay, so this is obviously 2 V phase I phase, and this actual kVA capacity of open delta is √3 V phase I phase. So that is √3 by 2, which is 86.6%. So we are able to use only 86.6% of installed capacity. We have installed 2 V phase I phase uh, capacity, but we are able to use only 86.6% of the total installed capacity. So that is one kind of loss actually. So that is one disadvantage of this open delta or VV connection. Is it clear?
Yes, sir.
Only you are responding. Any all others, they are not understanding
Yes, sir.
anything.
Yes, sir, we're getting it.
Yes.
Okay, okay, okay,
Yes, sir.
fine. So that is the utilization factor. So this means that full capacity of the two healthy transformers cannot be used in open delta mode. So this is one disadvantage of open delta connection. Only 86.6% of total available capacity can be utilized. Now individual shares of the two healthy transformers. What will be the individual share? So here VA shared by each transformer is V phase I phase, and total three phase VA supplied is this. So individual share is 1 by √3, which is 0.577. That means each of the two healthy transformer shares 57.7% of the total VA and not 50% of the total VA as anticipated. Okay, so here each transformer is sharing 57.7%, not 50%. Okay. In
Sir,
open delta mode, yes,
57.7% how?
yes,
Sir, 57.7% in both.
Yes.
So then the total is exceeding 100%.
No. Not exceeding. Here, see, each of the two healthy transformer shares 57.7% of total VA and not 50% of the total VA as anticipated. It looks like that total VA, see, total VA is 2 V phase I phase. Okay, we are using only root 3 V phase I phase. Okay, and share of each transformer is V phase I phase. They are supplying V phase I phase each, but we are not able to supply this amount. Getting my point?
No, sir. Not understood.
Actually, it would be 50% if this becomes 2. Then only we can say that shares of each transformer is 50%. But as we are capable of using less, that is why this percentage increases. Just a minute. If we calculate this percentage with installed capacity, then it becomes 50%. But we are not capable of using the whole capacity of the system, but the VA shared by each transformer is V phase I phase.
Hello, sir.
Yes, are you getting?
Sir, this VA shared is the supply voltage shared between those two transformer or the output?
Yes. This is the supply.
Yes, sir, then it is 50.
You are giving this amount of input, but you are getting this amount of output.
Yes, sir. Understood.
Yes. So now, in open delta mode, total load power need to be reduced to 57.7% to prevent overloading. Now, what if the load is not reduced? The simple answer is that the transformer will get damaged. Okay, but here we want to calculate that how much overloading will occur in percentage. Okay, so let us see. So percent increase in VA load on each of the two healthy transformers when connected as open delta can be calculated using this formula, that is VA load per transformer in VV connection and original load per transformer in delta delta connection divided by original VA load per transformer in delta delta connection. Okay, so here it is 0.577, and in case of delta connection each transformer is sharing 1/3, so 0.33, and therefore original load per transformer is 0.33. So the overloading is 73.2%. Okay, so that is a huge amount of overloading. So the transformer will get damaged. Okay.
Yes,
So
sir.
therefore, the same conclusion, each of the two healthy transformer will get overloaded by 73.2%. If the same load is continued, same load is means as per our example 60 kVA, if we still continue to supply this amount of load, each transformer will get overloaded by this percentage, that is 73.2%. And what will be the effect? Both the transformer will get damaged. Okay. So now the applications. So what are the applications of this open delta or VV connection? It is very simple. If any one of the delta delta connected transformer get damaged, then we can still be operative. That means we will be able to supply the load for the time being with this open delta connected system till the damaged transformer is being repaired. And another vital application is that, very important application is that, this open delta connected transformer can be used to provide service to a new area under development. Okay, so this is intentional delta delta connected system. What is that? Initially the load demand is less, which is projected to increase over the years. Okay, so we will start the system with 2 transformers only connected in open delta. Okay, so and as the load demand increases, we will connect the 3rd transformer to complete the delta connection. So this will save investment, because the existing load for a new area, for the existing load to that for that new area, only 2 transformers are sufficient. So if we use this complete delta delta connected system, then we will not be able to use the full capacity. So that is total wastage. Okay, so we can use, or we can start supplying with 2 transformers only connected in open delta, and as this load increases, the 3rd transformer can be added to complete the delta delta connected bank. Clear?
Yes,
Yes,
sir.
sir.
So when one transformers get damaged, that is accidental case, it is fine, but this is intentional delta delta connection we make intentionally, that is to save investment. Okay, so by adding the 3rd transformer, total load capacity of the system increases from 57.7% to 100%, that is an increase of 42.3%. okay, that means by installing the 3rd transformer, we are increasing the capacity of the system by 42.3%. so that is another advantage of this system. I mean, that is the most important advantage of this system. One advantage is that for accidental case, we can remove the faulty transformer and we can still be operating with the existing open delta connected system. Okay, that is one advantage, but this is another important advantage, that we can increase the system capacity by installing the 3rd transformer, by increasing the capacity to increase the capacity to 100%, that is an increase of 42.3%. Clear? Okay, that's all about 3-phase transformer. Now you note down this problem and try to solve this problem yourself. This is a very simple problem. Just you need to know the relation between this phase voltage and line voltage, and phase current and line current for different types of system. In case of star, it is VL equals to root 3 V phase, IL equals to I phase, and in case of delta, it is VL equals to V phase and IL equals to root 3 I phase. These relations are sufficient to solve this problem. Very easy. Okay, done. You can take a snapshot.
Yes, sir, taken.
Okay. Next, note down this problem also. This is a problem based on this open delta connection. Done.
Yes, sir.
Okay, so that's all about this transformer. So from next class we will start DC machine, and for your mid same exam the syllabus will be whatever I will teach up to 18th of February. Okay, we have 3 classes, so whatever we will cover during this 3 classes, that will be your syllabus.